Hello students, today our lecture is beta function. So what is beta function? Beta function is usually represented by the symbol beta Lm, where L and M are greater than 0, and it is defined by the definite integral. Actually, the beta function is a unique function where it is classified as the first kind of Euler's integral. The beta function is defined in the domain of real numbers. The notation to represent the beta function is beta, where L and M should be real numbers. The beta function in mathematics and physics explains the association between the set of inputs and the outputs. Each input value, the beta function is strongly associated with one output value. The beta function also plays a major role in many mathematical operations. So, to define the beta function, this definite integral, which is integral from 0 to 1 x to the power L minus 1 into 1 minus x to the power m minus 1 into dx. This is called beta function, and it is usually represented as beta Lm, and these L and M, they are real numbers. So if we are here Mn, so we should write Mn. If here is Pq, we should write Pq. So these are integers and they are actually real numbers. Now we are asked to evaluate the beta function in terms of the gamma functions. So now evaluation of beta function, or we are asked to, we can write it as prove that beta Lm can be written as gamma L gamma M upon gamma L plus M. So here is the proof. We know that by the definition of beta function, beta Lm can be written as integral from 0 to 1 x to the power L minus 1 times 1 minus x to the power m minus 1 into dx, where it should be remembered that L and M both are real numbers. So we can also write this as, by interchanging these functions, it can be written as integral from 0 to 1 1 minus x whole to the power m minus 1 times x to the power L minus 1 into dx. Then integrating by parts, that this is the first function and this is the second function. So this beta Lm is equal to the first function 1 minus x to the power m minus 1 into integral of the second function. So its integral will be equal to x to the power L upon L, and the limits are from 0 to 1 plus differential of first function, derivative of first function, which is m minus 1 into 1 minus x to the power m minus 2, and the integration of the second function, which is x to the power L upon L into dx. So by applying these limits, this term will goes to 0, because 1 minus 1 equals to 0, 0 multiplied by this term, and for the lower limit 1 minus 0 to the power m minus 1, and this will be 0 to the power L, so 0 will be multiplied with this term, again it will be 0. So by applying these limits, the whole term goes to 0. Then beta Lm is equal to m minus 1 upon, bring this L out of the integral, and it will be 0 to 1 1 minus x to the power m minus 2 and x to the power L into dx. Again integrate it by parts. So this will be now beta Lm, which is equal to m minus 1 upon L, and again this is the first function, which is 1 minus x to the power m minus 2, and integration of the second, which is x to the power L plus 1 upon L plus 1, and the limits will be from 0 to 1. Plus derivative of the first function, which is m minus 2 into 1 minus x to the power m minus 3, and integration of the second function, which is x to the power L plus 1 upon L plus 1 into dx. So again applying the limits to this term, this whole term will goes to 0, because here you see that if x equals to 1, so 1 minus 1 will be 0, so the whole terms is 0, and for the lower limit, when this x zeros, so the whole term again goes to 0. So by applying the limits, this whole term goes to 0. Then we are left with m minus 1 upon L, and here is this is in multiplication with this term, so this will be times m minus 2 divided by L plus 1, so bringing this L plus 1 out of the integral, into integral from 0 to 1, 1 minus x whole to the power m minus 3 and x to the power L plus 1 dx. So again and again integrating, you see that for the after the first integration we got m minus 1, and in the denominator we got L. After integrating for the second time we got m minus 2, and here we got L plus 1. So we see that m is decreasing while L is increasing. So after so many integration, we will be integrating again and again. We will have the equation like m minus 1 times m minus 2 times, and at last as we see that m is decreasing, so we will get to 1, and in the denominator we see that L is increasing, L times L plus 1. In the next step we will get L plus 2 and so on, so we will get L plus m minus 2, and here we will be left with integral from 0 to 1 x to the power L plus m minus 2 into dx, and we are left with the last integral, so this will be m minus 1 times m minus 2, and this process goes on to 1 divided by L into L plus 1, and this goes on L plus m minus 2, and by integrating this term we will get x to the power L plus m minus 2 plus 1, so this will be minus 1 upon L plus m minus 1, and here the limits are from 0 to 1. And bringing this L plus m minus 1 out of the integral, and this by applying the limits this will be 1, so we will have m minus 1 times m minus 2 times 3 to 1, and in the denominator we will get L times L plus 1 times L plus 2 plus L into L plus 3 and so on, and at the last we will get L plus m minus 2, and here L plus m minus 1. So here we see that this is actually a series of factorial, so this can be written as m minus 1 factorial divided by L into L plus 1 L plus m minus 2 times L plus m minus 1. If we multiply this equation by, let's suppose, L minus 1 into L minus 2 and up to 3 to 1, and similarly in the denominator multiplying and dividing with this series L into L minus 1 times L minus 2, and this is 1. So here we see that this is actually L minus 1 factorial, so this is m minus 1 factorial into L minus 1 factorial. In the denominator we will get this one is 1, here in the last we have 1 and then we have 2, so there is no problem if we write it from the beginning or from the last. So this is 1 2 3 and up to L minus 2, and then up to L minus 1 times L plus 1 times L plus m minus 2 times L plus m minus 1. So here we see that this is actually a series of L plus m minus 1 factorial. Here you can see that this is L plus m minus 1, then L plus m minus 2 and L plus m minus 3 and so on, then this value will reach up to m, so that will be will cancel with m, and then the value increases. So this can, in the denominator we will be, so by writing this L minus 1 before and m minus 1 after, and this is the L plus m minus 1 whole factorial. Now earlier in gamma function we had a property that gamma n plus 1 is equal to n factorial. In the previous lecture we discussed this property. If we replace here n by n minus 1, so put n is equal to n minus 1 in this equation, here n minus 1 and here n minus 1, so we will get n minus 1 plus 1, gamma n minus 1 plus 1 is equal to n minus 1 factorial. So this minus 1 plus 1 cancels and we are left gamma n is equal to n minus 1 factorial. So if here is n but here we have L, so this L minus 1 factorial will be equal to gamma L, and this m minus 1 factorial will be equal to gamma m, and here we will have L gamma L plus m. So this is our final result which we have proved. Now we have another property of beta function, that is to prove property of beta function. That is to prove beta Lm is equal to beta m into L. That is, we have to interchange L by m. So starting from the definition of beta function, that is beta Lm is equal to integral from 0 to 1 x to the power L minus 1 times 1 minus x to the power m minus 1 into dx, and here L and m are real numbers. This is equation number 1. Also we know that the property of definite integral, we know that integral from 0 to a, and we have some function fx dx. We can write this function fx as integral from 0 to a f of a minus x into dx. This is a property of definite integral. That means that here we have x and we will have some value of this integral. Here we have x. If we replace this value, this x in the integral, by a minus x, so there will be no change in the result of the integral. So using this property in the above integral, we will have, therefore beta Lm can be written as integral from 0 to 1. Here instead of a we have 1. So replace everywhere we have x, replace it by 1 minus x. So here we have x, therefore we will replace it by 1 minus x to the power L minus 1, and then we have here 1 minus x, and now replace it by 1 minus x to the power m minus 1 into dx. Now simplify it, that is integral from 0 to 1 1 minus x whole to the power L minus 1, and multiplying this negative sign with this 1 and minus x, so we will have 1, and this negative sign will be multiplied with plus 1, so it will be minus 1, and this will be plus x to the power m minus 1 into dx. Because if you are thinking that here is power and 1 also, so we know that 1 to the power anything, that is also equal to 1. So this will be now integral from 0 to 1 into 1 minus x to the power L minus 1, and 1 minus 1 will be cancelled, so we are left with x to the power m minus 1 into dx. Bringing this x to the power m minus 1 before, so this will be x to the power m minus 1 into 1 minus x to the power L minus 1 into dx. And you see that by the definition of beta function, here we have integral from 0 to 1 x to the power L minus 1, but here we have m minus 1, and 1 minus x to the power m minus 1, and here we have L minus 1. So we can write it as beta ml. Thus beta lm is now equal to beta ml. This property is called symmetry of beta function. Thank you very much.